Okay, I think now works.
Yeah.
Sorry about the muting. Okay, so I would like to get to understand this P, or at least some marginals of the P. And this is, let's say, my definition of quantitative understanding. So in this talk, what I will do is give a little bit an overview of what we have been doing in the measurement compartment. So how do we get information about the behavior of crowds? And since we are speaking about characterizing a probability, unavoidably this means doing a large-scale measurement, right? We have a complex probability landscape, so we can understand it only if we sample it hard enough. And then I will move to the modeling. And I will have different spins on how we model this probability, starting from very traditional physics. I will move to generative AI, and then I will get back to ongoing work that really use more, let's say, language of more traditional physics. And I will put this last aspect at the end because it's still really ongoing work, and I would keep it for last. Okay, there is some manual interaction here. Let me start from the characterization of this probability. So it's a physical system we need to measure. When it comes to understand crowds, there is a whole spectrum of things that are possible to measure the system. Here, measure the system means I would like to really take a crowd and being able to track people, to extract trajectories. And trajectories, if you will, is a decent minimum degree of freedom to explore. In principle, you can do more. There are more degrees of freedom, orientation, gaze, stride, and whatnot. But let's say minimum for me is being able to pick up trajectories. And well, maybe I need to mute the audio, but it seems too complicated, so I will hope it doesn't sound again. It doesn't ring again. There is a whole spectrum that has been going on in research, and it goes, from one extremum in which you take a very, very big hangar. This is done, for instance, at the Jülich Supercomputing Centrum. There is a very strong group on the topic led by Armin Seivrit. They would have huge hangars, and those hangars that are not occupied by the supercomputer, they are used to build, mock setup or where a large crowd could walk. And then these people would be tracked by overhead tracking. And let's say, based on the setup that you make, you extract some data. This is one part of the spectrum, and the other part of the spectrum is instead of being in laboratory, we are in real life. Yeah. So, and we try to extract measurement. So, why do I call this different extreme of the spectrum? Because we are talking about people, in principle, not simple to track, not simple to measure. I will say something later on. On this side of the spectrum, you basically are in a laboratory. You put yourself in the easiest possible condition to measure. You ask people to wear a vest, wear a helmet that is easy to track with the computer. And then you have full parametric control on whatever you want to measure. So you design the geometry, you set the flow, and so on and so forth. So 100% parametric control. What's the downside of this story is that first, okay, we are trying to probe the behavior of people, but here what happens is exactly what you ask people to do. So you will essentially measure, you ask people to walk in a corridor and, to enter from here, exit from there. This is what you measure, right? So let's say probability of measuring rare events is practically zero. And on the other hand, as I said, this is about probing a probability. This means sampling a system really, really a lot. And now here you might have 100 people, that you ask them to do something, and you can repeat the experiment twice, 3 times, and so on and so forth, 4 times. But then the day is over, and this is your data set, right? So how much statistics can you have? On the other side of the spectrum is real life. This is where we work. We displace the sensors in real life location. We track people person by person. We try to be as accurate as possible, and we let tracking system go for months, years. In train station, right? So imagine a train station, you gather 100K trajectories per day. After 3 years, you are in the many millions. You can do whatever sort of statistical analysis with, tails until the very far end. What's the drawback is you have essentially very little parametric control. Okay, so it's like you are in a station, whatever happens is what happens in a station. At 8, you have the commuters, very dense flow. 5 minutes later, you have diluted flow. Sometimes you have counterflow, and so on and so forth. So these are a little bit the two sides of the spectrum with their pros and cons. And what I'm going to discuss here is, let's say, what you get when you are in the very high statistics regime that you can gather in real life, and also try to, somehow extend the spectrum towards also the more parametric control. You will see later on. Okay, a little bit more specific. What can we do to characterize this probability when we are in real life? There are a lot of methods. I don't want to make this a talk about measurement methods, that I don't think is the most interesting thing. But let me just say that, let's say, there are methods to get data about crowds at a different level of accuracy that, over the last decade, as AI developed so quickly, became more and more and more accurate. This is an experiment that we did with a group at the IIT Madras. We tracked every person in a train station, especially the alighting crowd, and you see we can track now at the individual level with a decent level of accuracy, even in color cameras. And here the question was more like, to which extent we can nudge the crowd to have to follow specific indications, okay? And see that we are now in position to acquire data with decent accuracy in color. This is a technique, however, that is privacy infringing. So there are possibilities to, well, okay, here you get pictures about people. This is not always possible, especially Europe, GDPR, this would be completely impossible. So there are techniques that are, in principle, as accurate, if not even more accurate, that are not privacy infringing, but they are more complex. I will say something about depth tracking. This is the technique that we've been working on very, very much in the past years. But also some analysis that it is a little bit more coarse-grained is possible to acquire data. For instance, in a museum in Italy, in Galleria Borghese, we've been using a lot radio beacon. So essentially, guests were given beacons, right, when entering the museum, and the beacons were tracked across the museum. They were simple Bluetooth beacon, pretty much similar to what Mike did at the stadium. Although here we didn't track mobile phones, but really beacon, and the resolution that you might have is at the room scale. So where are people across the room? Here you have a resolution at more or less trajectory level, and then when we go into the depth field, you can have three-dimensional and even orientation position about the people.
If you track people based on color, that's not inherently privacy infringing, right? Or...
Well, why not inherently? I mean, let's say I would say it is privacy infringing, right? Because okay, depends on the definition, I think. But as soon as, so here in Europe, as soon as you place a camera and the camera somehow stores frames anywhere, this is already not allowed, let's say. Okay. In Europe, what is allowed is having sensors that should they use color information, this is used only, let's say, from internal hardware of the sensor, whatever happened there, and what gets out of the sensor are already processed data that have no more information than a trajectory. Okay, so let's say that, I don't know, you have FPGA inside or whatever, color enters here, there is a CCD, what needs to get out is just trajectory. This is what is possible. To be honest, this is also privacy infringing, because as of today, if you have a trajectory of a person and this person has a specific limping pattern, okay, you pick it up, right? So in principle, you can push it very far if you want. So it's a little bit of a gray area. When it becomes not gray area is two cases, if you will. So one is, of course, police is allowed to record and so on and so forth, but whatever is recorded by police is typically kept into closed rooms in which you can get into only if you have a very specific permission and the video is deleted the one day after or 30 days after, or on private soil. Like you have a big festival, Formula One, and so on and so forth. They're as soon as the visitors enter, they are basically signing an agreement that for their own security they are recorded, and so you can do whatever. This is
apply to train stations also, or
yes, train station is the same. What we can do in train stations, so this is a train station of Eindhoven, is track only with methods that never ever used color information, for instance. Okay, so let's say there needs to be a case made about sensors not picking up any recognizable trait. Although, as I just said, you can push it very, very far if you have a person that is out, sufficiently many sigmas out of the standard behavior, you would pick it up for sure. That's it. Please, Mike.
What about in private premises?
Private premises is okay.
It's okay, so it's just public, right?
Yes. Private premises essentially, like Formula One people, when they buy the ticket, they are signing the fact that, for their own security, things happen. And so when they step in, you make the rules. This is also Formula One, the big festivals like we did down the rabbit hole and so on and so forth, same thing, we can do whatever.
For example, if I walk into a shopping mall, the shopping mall is also owned by a private company.
This is true,
but I don't sign a contract when I...
Exactly, I think this is why, in principle, this cannot happen at this level. Let's say you are not color tracked into shopping, at least not in the way I would know how to do.
Even though I some sort of... When I step into a shopping mall, I know that this is private property of...
Yeah, but typically you would see signals like, okay, there is a security video being acquired for security reasons, but also underneath, that there is no addition about the fact that this will be used for purposes other than, checking whether someone steals and so on and so forth. So this is, I think, the current European status. To be honest, it's very difficult, even if you have a very good technique that is privacy respectful. It's very hard to make a case still. I guess for what you guys did at the Balmer Arena, this was very similar.
It was also a different time. So when we started, it was before the Wi-Fi things were being anonymized, so MAC addresses were being anonymized. And in the arena, what they had to do at the time was just put a sign saying you're going to be tracked. If you don't want to be leave.
Okay. Yes.
It got worse, and then GDPR didn't exist when we started.
Oh, okay, fair enough. Okay. Let me maybe say something real quick about how we typically acquire data. This is a technique that will pop up in different parts of the talk, but let's say only from the data side afterwards. But just to give you the gist of something that for us has been working very, very nice over the last 10 years plus. We work with depth tracking sensors. So what happens is that we displace the sensor overhead looking down, and this sensor, using different techniques, they wouldn't measure color, but they would measure the distance field between each pixel and the camera plane. So let's say this is a escalator and staircases in the station of Eindhoven. So this is this area, and so what you see here in color coded is how high each pixel is, right? So people here are red because they are closer to the camera, and then as you go down, their shade changes and becomes, I don't know, whatever, more bluish. But the thing is that there is never a color information being acquired. What the sensor measure is, again, distance, and this is typically done through a particular laser infrared illuminator that enables to reconstruct this information without color. Then we deploy this type of overhead sensor in big grids, and then we would reconstruct a single fused map of the entire geometry, right? So we have many sensors. They produce their own three-dimensional view of the world. We merge all the three-dimensional view of the sensors together. We get a unique 3D map. And from this unique 3D map, we have a computer vision algorithm that do the tracking for us. This is, you can push the accuracy very, very far here, even shoulder, skeleton if you really want. And it has a very good degree of anonymity. And that's why we could deploy in train stations, museums also, and so on. And again, we have this type of technique that work in train station when you get 100K trajectories per day. You build up big ensembles real quick. Yeah, okay, so these are some examples of this system being deployed. Yeah, we have had collaboration with Naturalis, train stations. This was, I don't know, I think Bruce Springsteen. This is Down the Rabbit Hole last year, and so on and so forth. So we have been acquiring data.
Did you have to hire the crane?
You know why there is a crane here?
Right.
Because this guy is me on top of it.
Did you have to hire it?
No, yeah, no. This is we went there when they were building, right? So,
Okay.
so this is yeah.
So you get data from in front of the stage,
Yes, looking down.
how people move during the concert.
Yes, yes. This let's say still not yet analyzed, but the scale is this one. Yes, so it's
Dynamics.
huh?
Yeah,
Mosh pit dynamics.
there are
In principle.
There are papers on that.
Yes, true story. Yes, and as I said, this summer we did the Grand Prix. There are a bunch of very crowded areas, and we deployed a new generation of our sensors. This is very wide range stereo vision up to the point that we placed sensors, 12 meters high, and we were looking at 2,000 square meter area with a single sensor.
Single sensor?
With a single sensor, yeah, I was pretty happy about it. We were even security providers for the event. So there, in the security room, there was our stuff. It was cool, to be honest. And yeah, so this is okay. Some of the things we were viewing, we were measuring real-time density, possibly broken by area. Although at this distance, doing individual tracking is very, very hard. So let's say density estimation easy, optical flow. So let's say the average flow in the image also easy, but single person tracking, at least for us, is still hard. So
You get a biasing error, I guess, as well, because the environment is going to get worse.
Yeah, let's say I need to be honest that okay, here we use a density estimation model. So it's something that essentially has this property that it generates a density map, and then you trace an area and you integrate over the area, you get the estimation of the count inside. I must say that is very, it's more accurate than you would expect. But clearly, okay, the further you get, it's we tested ourselves with handcrafted ground truth 60 meters away, and the count is still pretty accurate. So I think you are in the 5% error range. Yeah, so then this whole thing is in 3D, right? So we have all the 3D vision of the area, and yeah, we try to position people in 3D. But this is more or less what we do in the data compartment. So how we acquire data on the thing, right? And what I would like to discuss in the next part of the job is how do we use this to do some physics. I will start from something we did a few years back. So more, let's say, one-step physics approach. I will move into generative AI, and then I will move to something that is more functional level Langevin. But I would like to give an overview here. So I will start from something that is a little bit older. Okay, now we have. Okay, let me start with something that maybe all of you here know, or maybe not. So there was a moment in which this whole pedestrian dynamics business transitioned from being a problem in civil engineering to be a problem also for physicists. And this is, I would say, around 95 when the Helbing, that I guess everybody here or somebody here knows, right, from ETH, made this social force model paper. And basically they would say, okay, how about we model people as Newtonian particles, right? So there is a Langevin type of dynamics in which people are somehow interacting with each other through some force-like term that is then dubbed social force afterwards. And then the question is, to which extent a model like this can represent reality? So the good thing about the social force is that it can reproduce nicely some qualitative aspect of the dynamics. There are some emergent behavior that are very well understood by now. Imagine that you have two crowds, the blue people coming from here and the green people coming from there. they would go in different direction. Then the flow self-organizes in lanes, and then with models, this is measured in reality, metastable lanes with some persistent times and so on and so forth. And models as simple as this can already reproduce this type of emergent behavior, as well as the intermittency that you might have, for instance, when you have a crowd that tries to go through a bottleneck. So the time statistics becomes non-trivial, and a model like this can already do it. The thing is that from between 95 and today, we understood that this model is very good for qualitative stuff, but it has almost zero quantitative prediction capability, although this structure is used in many commercial software. So, true story to be told, when they designed Skipple, they use models like this that have received almost zero experimental validation, and this is used to test whether the evacuation works. So I hope we're trying to do something better, right? Because now... But okay, true story.
Also the big bridge in Mina.
Again?
The Jamrock Bridge in Mina.
Yeah.
It was also this.
Yeah, okay, there are more, qualitative models for this.
1,500 people died, right? So.
There is big room of improvement. Yeah, that's what I'm saying. Okay, but this is where the story starts, and then let me tell you what happens when you try at this level to fuse this type of modeling with data. Okay, and again, my perspective is that now we have very, very big data. Okay, start simple, very diluted flow, one person walking, what do you observe? Okay, you observe more or less the behavior of diluted gas. Imagine that here you have a velocity distribution, and the red, so this is in log scale, the red line is the longitudinal velocity the fluctuation, and the blue line is the transversal velocity fluctuation, right? This is the probability distribution, this is the behavior of, a standard gas, okay? So you observe Gaussian type of fluctuation around 1 meter per second in this direction and 0 meter per second in transversal direction. And already at this very basic level, there is something interesting. Okay, what is the, let's say, the rare event, the deviating statistics that you can observe in this regime is that every now and then, but with reproducible statistics, people, because of they receive, I don't know, a phone call or whatnot, they stop and they invert their trajectories, which you can see in the PDF by having a negative tail. Okay, so you have now a system that somehow is a bistable behavior. Either you go in front or you turn back, and then you can hop between these two stable states. And it turns out that a model a la Helbing is already able, with the right type of potential, to reproduce this type of behavior. And the only, thing to model, and here we can keep it really, really simple, is somehow the potential that regulates the propulsion of the system. Okay, so imagine that we model the system with a differential equation like this. So x double dot is the acceleration, is equal to a propulsion plus some noise plus some confinement term. And remember, we need noise here because the system is stochastic. So we need in the modeling something that generates the stochasticity that we see in the data. Okay, so the only thing to deal talk about is the propulsion, and it turns out that if you model this system with the simplest possible bistable structure, that is, you have a velocity potential that is a double well, and this means that when you are here, you walk 1 meter per second, and when you are here, you turn back. Now the system has, if you will, a dissipation structure that is, you try to relax to a velocity that you like, and the fluctuation or an excitement that is given by the white noise, whose only possible rare event is the hopping to the other well. Then you have this bistable structure. And then it turns out that something so simple, only calibrated to reconstruct the velocity fluctuation that you have around this 1 meter per second, gives already a decent, captures decently the statistics of the path inversion. So this is the Poisson process that you get when you look at how long do you need to wait before you observe two consecutive hopping events. Okay, so in this...
sorry, there's no well at zero velocity, like for stopping?
Yes, very good question. So let's say, I think here in the probability, you see this peak, right? So these are people stopping. Simplest model, where we ignore people stopping. Clearly, you can make this potential a little bit better. You add a well at 0, and you have also those. Here we studied only the bistable stuff. And I think here let's say the thing is, there is a system that has statistics that are somehow at the small scale related to the fluctuation in walking. There is a particular correlation structure in the process, right? And by essentially calibrating the fact that you have the right correlation for the forward walking, the right velocity distribution, you gather the hopping events, right? Without calibrating explicitly against it. And this is the plot that says essentially how many people you need to observe before you observe these 2 consecutive hopping events. This is also very reproducible. Like you observe whatever facility, a station, a corridor, and so on and so forth, you will get something more or less. I mean, the inversion events are uncorrelated, so you expect the Poisson statistics, and such a simple model can reconstruct. Let's say very, very easy, but this is the interpretation that we give to how can we make quantitative let's say, force-based model. We read in the system a collection of statistics, velocity, correlations, and whatnot, possibly real event, and we would like to have a model that, once sampled, reproduce this structure. Oh, clearly, I started at the beginning with the fact that I wanted to characterize the probability over the trajectories, and if I have a Langevin dynamics, automatically I can write an action out of the Langevin dynamics, and now I fully characterize the probability measure on trajectory space. And this is the traditional Franklin-Wenzel type of action, right? So this is, so let's say, the probability of observing a given trajectory goes as exponential of an action term, and the action is can be derived from the Lagrangian, from the Langevin, and something that reads like this. Why am I putting this here? Because in the last part of the talk, I would like to discuss more complex actions that you can get that actually try to reproduce the probability of routing, so of long-term strategic decision in crowds. But I would like to, so this is the simplest thing that we can do. And I will not enter into further detail about this, but this concept of force-based modeling, so stochastic force balance, you can push it quite far. So we studied with this class of models, people going straight, people that for whatever reason they take curved paths, and so then you make a Langevin equation in curved geometry. Please.
Can I ask you a question about the previous slide?
Please.
Does this formula hold for arbitrary noise, or it only holds for small noise?
No, this is the small noise limit. Then you need the Onsager-Markov correction if you have a larger noise. But let's say this is also more conceptual, right? So if you have a diffusion process like Langevin and the small noise limit, the probability goes as this, that is exactly how likely it is that you offset from the instant tone that you get at 0 noise, right? This is the quadratic offset.
Thank you.
So you can push the concept very much further, and you can still get models that reproduce the statistical patterns that we observe in terms of probability distribution of velocity, position, correlation, and whatnot, with people walking, for instance, on curved paths. So we're pretty happy. So you just make the model a little bit more complicated. You curve the geometry, for instance, and then you can get a good model for people working on curves. We have works on this type of regime in many directions. So conceptually, it works. Well, okay, let me skip this. These are further spins on the same type of stuff. Okay, so next step is essentially, can you start studying the interaction with the same type of modeling structure? Answer is yes. So in the previous slide, I was studying the single particle, so the free particle type of problem, so one particle walking. Here I moved to studying, for instance, the two particle paired problem, right? So how me and him, for instance, avoid each other. Okay, so imagine these two people would avoid each other, and it's possible to, first of all, measure this type of dynamics. We measure this type of dynamics thousands of times in a train station. tens of thousands of times, and then it's possible to cook a force-based model that reproduces the statistics of the system. And so imagine that before I had the Langevin equation that had the propulsion, that had noise, and I would add something about the interaction. And let me play the movie again. Yeah, so essentially the model is about how people would adjust their preferred paths given the fact that they see someone in front. So there is a state in this type of model that is your preferred path, and since you see someone in front, you would adjust your preferred path and you would keep on fluctuating around your new preferred path. Let me keep it super simple. Turns out that we can have a decent agreement with the data if we essentially add a fourth term that depends on vision. So imagine you have a view cone, and based on what you see in front of you, imagine that you are walking according to a preferred path. Based on what you view in front, you would update your preferred path on the side. And so this is carried as a state in the system, so the path that you prefer, this is good enough if the force is something that is exponentially decaying with distance. How do we validate this at the statistic level? So we have been looking at diagrams like this. So we have two people. On the x-axis here, I place the distance, let's say, lateral distance they had when they entered in the domain. So this is some sort of, scattering type of plot. So on the x-axis, I have their initial distance, and for instance, on the y-axis, I have the distance when they are closest. Okay, and so what happens is that if people were head-on collision, so their initial transversal distance was 0. Then what happens when they are closest in space is that they need to avoid each other, so their distance would grow. Turns out it's 75 centimeters. At a certain point, this thing became a big thing in the Netherlands, that people avoid each other in 75 centimeters. But anyway, so, and then this effect would essentially decay, right? Because if you have a very large offset, there is no reason why you should have interaction. And then it turns out that a model with the structure I discussed before can reconstruct the average behavior, the fluctuation behavior recently. So we said, okay, Langevin model works. We can push the concept further, but let's say as soon as you would like to do n-body type of interactions, things become immediately much harder. So now I would like to discuss two possible directions to do the n-body, let's say, type of structure. Okay. So, please.
So this data,
Yeah.
this is measured in a real situation
Really?
where there are other people around.
Yes.
And especially also, I can imagine that this avoidance dynamics will really depend on the density of people around you.
Fantastic. So, yes. Imagine you measure for, so this is, let's say, the diluted avoidance problem. Imagine that you have the data for 3 years, okay? Within 3 years, you have the privilege of saying, I'm only gonna look at pairs of people that avoid each other under the assumption that the closest other person is at least this many meters away.
Yes.
This happens thousands of times, okay? The next problem is how do you search for this event efficiently? That this becomes more a computer science graph query type of issue, but let's say there are sufficiently many events, thousands. Yeah. Okay. So this was that regime. Okay, I would say something about how to deal with n-body interaction. I would move to some AI stuff now and get back to the physics because this is a finished work, and then I would like to keep the unfinished stuff, for the end. I think this is an interesting spin on what we can do at the interface between AI and physics, considering generative models. This will place us decently in the middle in this spectrum that I explained before, because in the end, we will cook something that has the richness of the ensemble level information, but also will enable us to cook parametric experiments. And so this is, I think, a good construction. Okay, so the business here is to characterize the probability. And now let's say that I will still stick to a force-based balance type of approach. and I would like my generative model to be such that it learns to generate the conditional probability that the acceleration of each particle has, given the state of the system, that is the neighbor's position and possibly history. Okay, so now I would like to create a picture of the system by characterizing properly the instantaneous acceleration of particle, right?
By history, you mean just position or
let's say it's a sort of latent state that is cooked, considering the positions and velocity of your neighbor in the past many seconds. So you hold state with a given window, let's say, and this is what informs the structure. Yeah. So let's say if L being a model as an, let's say, additive force structure, okay, so this type of equation here, this additivity hypothesis is completely dropped. So in principle, the model can do anything without having any additivity constraint on the interaction rules. Let's say, okay, we used, let me say, here this model is trained with quite a substantial data set. This is a trained platform at the Eindhoven train station. 3 years of data, everyone is tracked. This is 80 meters, and this is maybe 10. Okay, part of this data set is publicly available. Should anyone want to play with it? Okay, so we are in the many millions trajectories. Okay, I want to stress something very interesting that will reconnect with these parametric experiments. I have a claim to make about this data. It's very heterogeneous. Anything happens in this data set. This means that this data set samples information about the behavior of pedestrians, dense, diluted, interaction, not interaction. So the information is there. It's just very, very hard to find. Okay, so it's like this is an ensemble of experiments that is just, and these experiments are very, very hard to find in a gigantic data set, but they exist, even with many, many repetitions. So the issue is now, can we essentially go efficiently through this data set with the generative model? Okay, so what we cooked here was something that then eventually we named the neural crowd simulator, whatever funky name, but it has these specs. So it's a stochastic, so it's a generative model that deals with n-body interaction and works as a dynamical system. This means that it's an autoregressive model, so it's a model that, how to say, given the history, past step, generates or samples information about, autoregressively generates information about the next step. So there is a combination of a generative model that is done with a conditional variational autoencoder, and the interaction is managed through a graph neural network in an autoregressive approach. Okay, so whatever. Qualitative picture. Okay, this doesn't say much at this level, but imagine ground truth is here. So these are different scenarios. Now the model is essentially trained to sample the statistics of the system and initialized with an ensemble of initial conditions. So I tell you where the people are born on the station, and the task of the model is to step them forward according to the statistics that is present in the data. Okay, simulation is here, ground truth is here. What happens is that the system has a state. Okay, there is an underlying graph neural network that defines connectivity up to a given range. There is a message passing step, so the particle can exchange information about their let's say personal latent variable. This is used from each particle in a variational autoencoder fashion to sample. Okay, what is the stochastic next step? There is a next message passing step that is whatever is sampled is passed to all the neighbor, and this is ultimately used to determine the acceleration, and then the system is stepped forward with just explicit Euler integration. Okay, right. So this is ground truth. The simulation looks okay, but okay, maybe we're a little bit more serious than that. So okay, the movie is nice, but we are happy because this type of system captures the statistics of the system for real. So these are, for instance, probability distribution of velocities in linear scale, logarithmic scale. I think, yeah, fundamental diagram. So let's say this is how much the velocity and the fluctuation on velocity scales with density, comparing model and reality. So, okay, we have a whole ensemble of statistics with which we validate the model. So streamlines, strict lines, correlation functions, and so on and so forth. We were happy because we said, okay, we have a generative model that does something beyond capturing MSE, so the mean square error. Nice. We have a decent model. I think the interesting question is, can we use to understand something about the physics of the system, right? So we have complex stochastic behavior. Can we do something interesting about it? And this is what will place us in the middle in this ensemble. So, okay, imagine when you do, physics as it has always been done. There is a moment in which you create a model, you validate the model, and then you analyze the model, and then you try to understand something out of the model analysis, bifurcation and whatever. Now, with this type of AI model, analyzing the model internals is typically hard. At least for 99% of the model, I don't know how to do it, right? It's, let's say, typically black box type of structure, if not for some symmetry that you put a priori inside the model, some whatever, rotational, translational symmetry, and so on and so forth. So what can we do? This is what we did. So we said, my original claim is that in my data is an ensemble of very diversified experiments that are just very, very hard to find, okay? So what if we now use the model to cook somehow in vitro experiments? So I place my particle, so I would like to study interaction, very good. Then I create, let's say, surrogate experiments in which there are particles interacting, and then I will study the response of the model to analyze how, for instance, the n-body particle interaction works. So I would use the model, I would sample the model to study this n-particle interaction regime, okay? Sure, I have a model, I can place my particle wherever I like, I can step the system forward, I can measure the behavior. How do I tell the thing is real? Okay, the model will do something, but it can hallucinate, whatever. So how do we tell the thing is real? Well, we do what is reasonable. We try to see whether this model can reproduce experiments that have been done previously and that were not part of the data set and the model has not been trained with. So can this thing reproduce something that we already know without it being trained against it? Yeah, turns out we can. For instance, we considered the case of the avoidance that I explained before. So the avoidance statistics, so how two people would sidestep and so on and so forth. So we cook virtual experiments in which we ask the model to reproduce this avoidance scenario. And also there we could reproduce the statistics that we had measured previously. So for instance, this is a scattering type of problem. So how do people would avoid one another when So this is again, as I said, transversal distance. This is the transversal distance when they are closest. And we plot statistics that we had from previous experiment. We were pretty happy about the fact that without any explicit training, we could reconstruct things. Good. So I said, okay, then let's see what happens if we ask the model to look into a regime that is actually interesting, that is the n-body interaction regime, okay? And again, what am I going to say is cannot be a definitive answer, right? Because then we need to make an experiment, but at least we have an idea of what we could expect in a way that is hopefully compatible with the data. Okay, let me skip this. These are just statistics of the pairwise interaction.
Was it a problem because it systematically overestimates the transversal, right?
Well, okay, but let's say, yeah, okay, let's say, sure, depends if we want it on point. Consider that this is the typical fluctuation that there is in the physical process. So this is the error bar of the physical process, and this is the average prediction. So consider two things. You're correct. The average model overestimates the data, but for instance, the data is not correct beyond 1.5 meters. Why am I saying so? So these are two particles that are initially 1.5 meters apart. And now you see that when they are closest, their distance would even reduce. This, I mean, you expect that the farther the particle get, the more independent they get. So essentially their average should be unperturbed by the interaction. This was not happening in our 2018 data, and this was an effect of the fact that geometry was finite, so that the particle could not get apart. And for instance, this is an effect that in this new data doesn't exist. So the asymptotic trend, for instance, is correctly reproduced. Here we don't have 75, we have 78, and here, okay. But let's say, definitely we are within error bar pretty strongly, I think.
So that was another question I had before, but how sensitive is the model when you calibrate it on different data sets? Because I imagine if you've got a constrained geometry, this lateral movement might change, right? So is it, if you retrain this on your Grand Prix data, would it be better?
Okay, this is a very good question, and it's something that I cannot do because data sets of the same magnitude of that we have at the train station don't exist.
Yeah.
Exactly. Okay, let me tell you what we see when we try to cook an experiment in which there is n-body interaction. But this is a big problem, right? So in principle, in this active matter, you would like to understand whether the interaction is metric, as they call it, so depending on distance, topological, depending on number of neighbors, and how does it scale. Okay, we can at least ask our generative model to deal with the question, okay? What's the hint? Okay, helping type of model would have a response. So this is the acceleration of the particle interacting with another particle, and let's say the helping response is a linear response. The more the number of neighbor, the larger the response. Okay, and we use our model and we get something that is a thresholded response after a critical n. This is, by the way, compatible, for instance, with what has been measured for birds. So birds have been measured to interact with finitely many neighbors. I think there is, I don't know, 5, 6. This would be 11. But at least it's a consistent trend. There is a finite type of interaction structure that is indeed compatible with the top K social force type of structure. So a saturation of the social force at critical K equals, I think, 11 or something. So we were pretty happy. Let's say we can use this generative structure to try to at least nudge where to look next into this type of problem. That I think was a good step beyond just a claim that the model does reproduce reality nicely. Yeah, okay. Bunch of statistics. Okay, I figured that I don't have time left, so I would have had something about fluctuation at longer scales. So maybe I will shrink this part.
You still have 10 to 15 minutes.
10 to 15 minutes. Okay. Okay, I'll keep it anyway short. So here I would like to step back to physics again. I said my initial goal is to characterize the probability of trajectory. We did the Langevin model that is essentially sort of one-step Markov type of model, right? Here is, can we characterize the probability landscape on the longer scales? And the problem becomes immediately routing, right? So in routing, somehow you have concatenated decisions. I mean, routing is the expression of a strategy. You would like to get from A to B optimizing some functional, so being there fast. And being there fast means, okay, you don't want to bump into obstacles, but if some roads are trafficked, then you pick another roads, right? So there is now more like, yeah, if you will, mesh type of structure, right? So if there is a road is empty but is longer, is maybe better than a shorter road but full of other people. So can we get the statistics? So then the modeling perspective here would be the following. So we have particles, and the system is regulated by an interplay of two things. That particles, on one end, they try to pick for trajectories that minimize the cost, for instance, minimal ETA, distance with the others, no sharp turns, and whatnot. So this is what gives dissipation structure. But on the other hand, we expect the system to be stochastic. And so I would say we fail a bit in the process of optimizing a functional. This means maybe we don't pick optimal choice because there is insufficient information, we are distracted, there are variabilities between different subjects. And so as a whole, this is what will give me a noise structure. So now I have an interplay between the willingness of optimizing and the fact that I fail because of whatever noise source. Okay, so now I have immediately, let's say, a sort of stochastic gradient flow type of idea. Okay, so there are two key questions. So one is more a system identification problem, that is, given the trajectory, what is J? So what is the functional that the trajectory are trying to optimize? And the second question is how to deal with the suboptimality. So how to deal with the fact that despite a J exists, the trajectories won't be able to actually optimize for it. Okay. So here we started a few years back with the much simpler version of this, joint optimization problem with the prototype of routing. That is, imagine that you have two paths, A and B. This was GLOW, so the biggest festival in Eindhoven. You get 130,000 people in a week that go around the city. This is the Philips Stadium, and we had people that had to follow two paths, one that is short, so to get here, so in principle preferred, but then this would saturate and people would take the other one. Okay, so this I would say is the prototype for routing. Okay, and we decided to again, we have a variational model, right? So this model based on minimizing a functional. So A and B, and then here, what's the simplest model that we can cook, or what are the simplest observables or the simplest marginal for this system are the following. Imagine that I take an overhead snapshot of my system and there are n particles inside, so n people, and then I simply count how many take NA, so how many people take the straight path and how many people take the detour. Okay. So let's say the average picture looks like this. So this is n, how many people, and the red dots are the people that take the short path. And then this grows linearly, so everybody takes the short path should the short path be sufficiently empty. And then there is a kink because the second channel starts to fill. Okay, so now you see that the system, when the short path gets suboptimal, equilibrates automatically between the two paths. The thing is that, again, the system is non-deterministic, though, because now here the blue shade are, let's say, events. So if the bullets is the average behavior, the blue shade here is the full probability of the number of people in the long path. And we see, for instance, that there is herding effect, meaning that even if at the given number of people the short path becomes suboptimal, there are still conditions in which everybody blindly follows the other into the short and clogged path. And this is an intermittent structure, so it's also it's non-trivial time statistics. Okay, what is a minimal model for this? Well, what are the characteristics of the system? So somehow we expect on one end that the more people in a channel, the slower they go, right? So this is in traffic is typically called fundamental diagram, density versus velocity, higher density, lower velocity. This is also measured in the two-channel velocity drops, and velocity is non-deterministic, right? So there is a given velocity fluctuation. So simplest possible model, we say, imagine that we have a state that are the n particle and they need to make a binary choice, A or B. And then the question is, can we have a model that once sampled gives the right statistics between the A-B choice? So these are n distinguishable particles. And they are distinguishable, for instance, by the fact that they would walk a slightly different velocity from one from the other. So each particle now tries to get on the other side in minimum time. So there is a cost minimization that is given, for instance, by time. This is in our modeling. And then the more particle in a channel, the lower the velocity. And the randomness, for instance, is given by velocity fluctuation, the fact that each particle would go at slightly different velocities from another particle to mimic this diversity. So this means that the right transition moment is random. It's non-deterministic anymore. Plus intermittent herding. Okay, so now we model this system as with a single functional, let's say, and the functional, let's call it J, is the sum of the traversal time of each of the particles. And remember, if now your traversal time depends on two things. If you go on the longer path, your traversal time will be longer. For instance, LA is the length of the short path, LB is the length of the long path. So naturally, the longer the path, the longer the traversal time, and the time is then length divided by velocity. This means that, in principle, the more people in the same channel, the lower the velocity. So the claim is the system tries to minimize this functional. So the binary choice is such that this is minimum. I would like to make a statement for people here that are more into Nash type of structure. This is a cooperative assumption, so the system collaborates to minimize the functional. I would like to make a claim. We try to model this system as a Nash equilibrium in different ways. I never get to have a Nash equilibrium model that behaves better than the model that I'm going to explain. I don't know why, but yeah, maybe this is a point for discussion later if there is someone into game theory type of stuff. Okay, so we have a system level cost. Velocity is something that decreases with the number of people and fluctuates stochastically. And okay, let me skip this. What happens is that a model as simple as what I just explained can really express the fact that the system has these different regimes, and then we start from filling one channel, and then all of a sudden, in a smooth way, when the channel is filled, we shift to use two channels. And actually sampling the model, we can get this intermittent usage of the two channels. So we were pretty happy. This was a simple model, only binary choice that once sampled recovered the bunch of statistics that we were looking for. The only surprising thing is that this was a cooperative dynamics for a process that I expect to be competitive. Let's say now we compete to get on the other side in minimum time, and so I would expect more Nash structure, which I couldn't recover. That was a little bit mysterious for me and still is. So I have students that tried different spins on this problem, none yet did better than this. So maybe in the end is a cooperative dynamics. I don't know. Well, maybe very last thing is what happens if we want to use this idea of cost minimization to predict entire trajectory, right? So now it's not anymore predicting a choice, but is to predict the strategy, right? So the long term. This is ongoing stuff, not yet published, but I would like to give the gist of the type of data we are looking at and the type of modeling, and then I will finish. So we are looking at two classes of problems. One is I have one person that walks in a crowd of standing people. Of this, we have also unlimited data. In a train station, there are a lot of cases in which people just wait and someone goes through. And then a second case in which we have people that interact with the geometry, and we can well, okay, this is a library of Twente University. We made a very funky experiment in which we tracked everybody in the library or in the entrance, and then we wanted to study the interaction with geometry, and this means that there was an obstacle, typically a table, and its position changed once per week. So this means that every week there are 10K people entering, and then the same people exit because there is only one access point, and then they would interact with this geometry, and then every week it's moved by an epsilon. So about 10 centimeter, 10 centimeter, 10 centimeter. And then you generate a grid, and this you can use to disentangle the effect of this specific obstacle from the rest of the geometry. Okay, so what happens? This is the class of modeling we are working with. So we postulate that the trajectories optimize a given cost, or the paths. Okay, so here I move from trajectory to paths. This means that I only look at shape. Okay, I'm not looking at the time structure. Okay, so this would be an integral in, let's say, the element of line instead of the element of time. So okay, this is also called geometric Lagrangian or Lagrangian density. And then we make an assumption, and we say, okay, how do I choose a path? Okay, so we say the path tries to minimize the functional, and then we try to be as simple as possible. We say, okay, I would like to get from A to B in minimum length, and so this means that in my integral I put a 1, right? Because I integrate over the trajectory a constant, and then I get the length. Okay. So among all the possible trajectory, I would like to minimize length. Typically, people don't do weird stuff when they walk. And so we introduce a penalty inside the integral that is the local curvature, right? So you don't expect to take super sharp terms. And this is this type of terms is present in papers that really study properties of locomotion on how people try to keep curvature low to be energy efficient. So this is the local curvature of the path. And then some interaction terms with the obstacles or with the standing people, to which we give an additive structure. And the problem is that these terms in principle depends on weights or parameters. So let's say that there is a lambda 1 in front of the interaction with the obstacles, lambda 2 in terms of the penalty to the curvature. Okay, and the problem is that we don't know.
One technical question. So I guess with your head tracking or your 3D thing, you're doing some smoothing on the trajectory, right?
Correct.
So how does that affect the local curvature?
This is very okay. Okay, so.
Sorry.
No, this is okay. I'm trying to gauge the exact, let's say, technicality. Okay, so this is a system. I mean, a measurement system. Therefore, there will be error. Fact. Okay. So we smooth using typical time filtering, and okay, there are two key choices: Savitsky-Golay or Butterworth filtering. Let's say we typically chop off frequency that are known to be beyond the swing. The swing. Yeah, exactly. So this is about 1.2 hertz. So this is 1.2 hertz, and we typically filter beyond 1.5, 1.6 hertz.
Okay. So this is kind of the limit for this local curvature.
Exactly. So you will not get faster effect because of the filtering. Okay. So this is my cost. Okay. Problem 1 is, can we identify the terms of the cost? And problem 2 is remembering that the system has a stochastic structure, okay? So here my claim is that, and this is somehow formalism that is used, for instance, to study phase transition, is at the same time, in trajectory space, what I say is that the trajectory as an object of my space is picked in such a way that a trajectory that goes down the gradient of this cost is better, right? So I have a gradient descent term on one hand. So this is a dynamical system in trajectory space, right? So each point here is a full trajectory. So S, if you will, is the coordinate along the trajectory, and tau is the coordinate that moves from one trajectory to another in trajectory space, okay? So this is now a gradient flow in trajectory space. And I have now a contribution that, given one trajectory, pushes me in a direction in which I have a trajectory with lower cost, right? So this is just the functional derivative of the functional with respect to the trajectory. And so this is just parallel to the Euler-Lagrange of this functional. Plus, instead, the fact that I say we fail in minimizing this functional, and let's say that in space now there is a sort of fluctuation field, or sort of noise field, that is delta correlated in space and time, and that forbids me from actually getting to the lowest point of this functional. And then we say, out of this Langevin equation, or overdamped Langevin, I study, let's say, the thermalized state, right? The long tau limit, which is essentially the measure that you get when you only look at the fluctuation when this disappears and these two terms interplay. So fluctuation and dissipation interplay. So now this immediately gives you a probabilistic structure in trajectory space that is just the Boltzmann measure in trajectory space, right? So we say a trajectory for which the cost is higher is less likely to be observed than a trajectory than the cost is low, and we have a temperature parameter that essentially gauges the degree of suboptimality. So the higher the temperature, the more likely it is to pick suboptimal choices. Okay. So we study then trajectories with this formalism, for instance, of people, going through understanding people. Or again, as I said, the obstacle problem, here are many table position and such. So also here, we have very, very many trajectory. This means that we can actually look at, let's say, the Fokker-Planck level behavior of the system, right? So how the probability really moves, or how the flow of probability is changed by the change of geometry, okay? And so, okay, there are two decent good news. The system seems to be identifiable with respect to this type of functional. What I mean is that what one does is that this functional depends on parameters, okay? And then the idea is to now pick parameters such that the prediction of the model is metrically closest to the ground truth, or the ground truth as the highest likelihood, right, of observation. And then what you see here is, let's say, some degree of score in parameter space for the parameter value when, for instance, one aims at minimizing distance between the trajectory prediction of the model on the ensemble level and the ground truth, or maximizing likelihood. They should be the same, depends on your definition of likelihood, but in principle, the idea is that what you observe is a sort of convex profile. So it seems that there is a choice of parameters that behave better than the rest. And in fact, okay, let's say this is the maximum likelihood story. Okay, this is minimizing error. Maybe this forget for the moment. So these are trajectories sampled. This is the heat map of trajectories sampled by the model. And then this is the ground truth trajectory. So let's say, look, for instance, this case, the black one is the ground truth. And the model would sample trajectories that are around the ground truth, which made us very happy. But the system here, for instance, is clearly bimodal or even multimodal. It's not that the trajectory below here is incorrect or impossible. It's just that time this was observed, right? So say, with the level of fluctuation in the system, we were pretty happy to observe things that were compatible with the data and with our experience. I mean, same in the obstacle problem. Let's say there is a choice of parameter that seems to behave better, and the choice of temperature that gives a degree of fluctuation that is compatible with the data. So this made me happy about this type of modeling structure. Right, that's that. It took a lot of your time, but maybe just to conclude, so the message is, first, okay, we can do some physics about crowd because the data exists, so we have a very large data set. Force-based model are maybe the more classic things that is possible, and so it's possible to push Helbing model in a direction that is quantitative, should the system be simple enough. I hope I showed an application of generative AI that enables to do something more interesting than just reproducing the system. And I think the step to scale up is this variational direction, in which there is a coupled system that tries to cooperatively or competitively trying to minimize functional. Then, of course, I'll be happy to chat about any of this. Let's say I also do some stuff about machine learning and fluids. If there are people who do similar stuff, I'll be happy also to chat about that. But for the rest, thanks for your attention.
One question?
This is me.
So thanks a lot for the talk. That's very interesting. I was just wondering, like you talked about this Langevin type equation to get the proper statistics of trajectories.
Right.
I of course, it's hard to get anybody in there. Is there also work going, like maybe from the other end, maybe first doing a sort of hydrodynamic approach and then adding fluctuations to the hydrodynamics, like a stochastic PDE type of modeling?
This is a very good question. Okay, there is a. Okay, I think there is a huge literature from, let's say, the mathematician side that covers the part about good definition of possible definition of PDE. They immediately go into the shock type of problems, right? So from shock wave that you get in traffic. So there is a lot of study there. I think, and Milfield limit also type of literature, of course, is there. I think there, I would say the quantitative direction is lost pretty quickly. Let's say these are then, I mean, you go immediately into the analysis of the PDE rather than trying to match something. There is, I've seen recently a very interesting work, also semi-quantitative on Milfield games. That means now you have a system that is expressed in macroscopic scale. So you have a density, but now you say the density. You say the density is like the one particle marginal of the system, and this one particle marginal is the marginal of a player that plays against itself, that is, or plays against the other, but the others are nothing by the density of himself. So it's a mean field, and then so this was able to reconstruct decently some interesting behavior, like the fact that when there is a huge crowd that wants to go into the metro, the first one go inside, and then at a certain point someone realized that it won't fit, and so they would step back. So this is work by the group this is okay, wait a second, Denis Ulmont, so people in France, Cécile Perroland, that have been looking into this stuff. The fluctuation part in stochastic PDE, this is what I always asked, but I have not seen anyone trying to do something interesting on the stochastic PDE part, to be honest. I'm very interested as well. I'm not a pro, I mean, by any chance, by no means I'm a pro, but this is something that interests me, but I've not seen anything clever in that compartment yet.
For the Phoenix Stadium experiment, you showed a cost function, which was this L over V.
Yes.
But you also showed these Herb phenomena. But so these in the modeling, these are not accounted for, I guess, because they're like anomalous.
Okay, no. These are accounted for. Okay, I didn't want to enter into too much technical stuff, but let me say what was the trick there. And again, okay, what was the trick first? So there are two paths, A and B, and essentially, if you will, the system, the only relevant parameter is the ratio between the two paths. Okay, then it becomes dimensionless given the ratio. So, what the way to get the Erding phenomena was to say that the ratio between A and B is regulated by a stochastic variable. Okay, so something that has a very long tail, if you will. And then that the system, once sampled, tries to gauge the ratio between the two paths, most likely will observe the right ratio, but every now and again will observe a very distorted ratio that implies that everybody goes in A. So there is a good thing and a bad thing. The good thing is that you can make a physical argument to actually measure from the velocity this sort of expected ratio, so you can probe this probability of expected ratio from the distribution of velocity. Okay, you can make some trick to infer this probability distribution. The bad thing, so then you get the right statistics and so on and so forth. The bad thing is that you would like to get this this herding more like an emergent behavior rather than some stochastic variable injected into the system. We tried whatever could come to my mind. The fact that, for instance, people stick to groups and then breaking a group is hard, or let's say introducing a penalty for choosing something different from the average, right? So like a consensus type of thing. I couldn't get anything that works decently. So game theoretic or cooperative. So I'm still in the quest for looking for something emergent. But okay, now we have something based on TASEP. If you guys know, it's this totally asymmetric exclusion processes. And now there is a crowd modeled as agents that are stepping through this TASEP, and at a certain point the TASEP bifurcates into two. And then, okay, there with the right rule, we can get herding as an emergent behavior, but this is still ongoing.
Not 1D, it's 2D or 3D.
No, this is a 1D TASEP, but let's say a sort of graph-like 1D TASEP that is like, so the state of the system is a TASEP like this, and then at a certain point, you have two options. And then when you are here, you need to decide, essentially.
The paths are linear, but it's emerging graph.
Yeah. Yeah, exactly. There is a choice process based on the scope of the system. This works better, but it's also much more complex than this. So it's weird.
Yeah, I'm trying to make a connection with other trajectory-based methodologies. But so one thing that wasn't clear to me is actually, do you direct your all your trajectories towards a certain endpoint? Do you really want to be there, or does the system actually spontaneously go there?
So
is that so? For example, all these paths, they end up, or all these trajectories end up exactly at the same end. So why doesn't it then wander off in the other direction?
Very good. So thanks for the question. Okay, so again, this is let's say a system in which we have all the trajectories, and let's say base modeling strategy is now I take all the trajectories that are born here and finish in a given region, right? So now I constrain the system. So I consider, let's say, a conditioned version of the system in which the trajectories are born somewhere and they all finish somewhere else. Okay, and I model what's happening in between.
It's the external, this is data.
Well, the data goes everywhere, right? I mean, essentially, the data can go here, can even go here.
Or is it a selection?
It's a selection, right? So I'm conditioning it to a specific type of origin-destination structure. I would say that, let's say, this is, when you enter this library, this is what you do. All the rest are very weird combination, but they're not impossible.
I have a very simple question. So, traditionally in the crowd literature, also with social force, you separate these two processes of deliberation, so goal selection versus kind of group choice. I think this is one of the big differences between the computational soft matter kind of stuff, where even with active matter. With humans, there can be a change in direction which is completely non-external, right? So you just, and the first stuff that you showed with the stopping, right? We did the work in the arena also on the levy dynamics. So for me, it's still always very hard to distinguish what is the deliberative process, because I could model that stopping behavior in a levy-like thing, just okay, this is not my route choice, but this is really the destination choice. So it goes to Peter's question, you know, how do we pick these things? And a lot of the things for the MotoGP, sail, and things like this, the dynamics of the crowd are less important for safety and things like this than where people are deciding to go. And if everyone decides to go to one exit at the same time, that's what causes. Okay. I think. Can you get? So I didn't really give you a question, but can you somehow use your data to try and infer these dynamics? Do you have the right scale? Do you have the right?
But I think, let's say. Well, okay, maybe I need to go here. I think the thing that is.
I guess the things that you did at the Light Festival.
Yes, I think this is the closest thing to what you're asking, right? So that is how much the self-interaction of the system modifies the outcome, right? Yeah. So I think. I mean, these are the hardest data. I mean, to get and to analyze, right? Because you have coupled and body on large scale, right? Okay. I'm not sure whether there is a good question. I can tell you what I'll be doing about this stuff is again try to gauge to which extent this behavior can be modeled as a joint or competitive minimization. This is what I think is interesting, and what gives spice to the problem is how to make this type of equilibrium system, how to study the randomness, right? In the sense that now it's a random equilibrium problem of competitive agents, and so this is, to be honest, what I'm interested into looking at. But let's say developing the right formalism is the first step, and this is what happened there.
I had another question actually relates to you. You discussed you handled or discussed a lot of different aspects, which you didn't talk about things like fluxes or rates or events per second. So why not? Is that not interesting, or is this not important? Is the amount of people per second not important? It's just the density. I mean, I don't know. Actually, this is a question.
I mean, you just sort of like
you want
pressure.
So how do you think about how many people have to be pushed per second through a certain corridor? Is that something?
Okay.
Really important?
No. Okay. Let me say.
Do you see where I'm going? Because sometimes you have these narrow, doorways where everyone needs to go through, and of course, the flux of this is extremely important.
Mm-hmm. Okay, what can I say? Okay, so I would say from the engineering perspective, the first order description of the traffic connects exactly the two variables that you are mentioning. One is density and the other is flux. Okay, so let's say if you forget anything about accurate measurement and so on and so forth, so the order zero description is a plot like this, in which you put the density here, and for instance, you put flux. And the density is people per square meter, and this is, I don't know, how many people per second through. Then, okay, you observe this.
Yeah.
Okay. And, okay. Now, maybe I can.
It's important, right?
This is important. This has been, let's say, extensively measured in a sense, right? So this has been characterized more or less in the shape. It's relatively universal in the sense that, okay, then you might have some fluctuation, but if you look at the averages, it's relatively robust. I mean, you know that this is maybe so the capacity is between 2.5 and 3 people per square meter, and then essentially the marginal gain of adding one more person is negative, right? So, and let's say there are two truths, I think, when you look at people, especially in real life. So, all right. So there is very interesting physics here, but it's also surprisingly rare to measure. For instance, in the Netherlands, in the sense that if you look at the train station for years, I mean, maybe you get here. So let's say you would find the countless paper that studied and made mathematical models about this regime, but it's really hard to observe unless you are at in the Ash, for instance. Okay, so even the Grand Prix, I mean, when the race is finished, like you have 100,000 people that want to get in the train as fast as possible, you will never observe 4 people per square meter. It's like
also a very bad situation to be in.
Yeah, no, this is for sure the case. But I mean, I'll tell you what. Let's say when we were working at down the rabbit hole, so we had sensors also at the gates because they wanted to understand whether they were doing the gates right. So whether the size, the width of the gate was okay. But I mean, to my surprise, when people get away from Bruce Springsteen, they want to get on the train and whatnot. I mean, here. Like and so I said, okay, I think here, real life, this is very hard to measure. Okay,
people in front of the stage, are they there? Are they anywhere close?
Okay, they're not trying to go anywhere though, so the average velocity is 0. Yeah. But maybe okay, I'll tell you something. Okay, this is going to be surprising. So at a certain point, we were in business with the municipality here, And the municipality here knows that there is a place not very far from here in which the density, especially at nights, get high because people are interested in stuff. And okay, so we deployed our sensors there in a very narrow alley that was maybe 2.5 meters. I mean, even then, you're still here. I mean, okay, the only interesting thing was that at a certain point you were changing from unidirectional to bidirectional, right? So you had a little bit of, I don't know, semi-rheology-like type of stuff, but I don't want to say that this is not real because it's definitely real, but the probability of observing this in the Netherlands, let's say, it's not so high to my...
In India, no.
Yeah, true story, yes.
Yeah, we observed a lot in India.
Yes, true story, yes. Okay. And but okay, this is let's say I would say the basic characterization, and also what is used for some dimensioning, right? You say, okay, I expect this. I would like my people to get out of the stadium in this much time, and you use this type of diagram to gauge how many exits and.
Any other question? Okay, yeah.
Thank you.